Picture this. You're standing in the middle of a crowded street, the hum of the city buzzing around you when suddenly everything goes silent. The cars vanish. The buildings morph into unfamiliar shapes. The people around you are dressed in clothes from another era. You've just stepped into the past, or maybe the future. Time travel has always been one of those ideas that sparks our wildest imaginations, from blockbuster movies like Back to the Future to mind-bending paradoxes that leave us questioning reality itself. But here's the thing, what if time travel isn't just science fiction? What if the universe has its own set of rules that might make it impossible? That's where the chronology protection conjecture comes in. This isn't just about whether we can build a DeLorean or stumble through a wormhole. It's about something deeper, the fundamental laws of physics, and whether the cosmos itself would ever allow us to twist time to our will. Think about the grandfather paradox. If you went back and accidentally prevented your own birth, how could you have traveled back in the first place? The universe doesn't like contradictions. And according to some of the brightest minds in science, like Stephen Hawking, nature might have a built-in failsafe to stop time travel dead in its tracks. That's the essence of the chronology protection conjecture, a theory that suggests time travel could be fundamentally forbidden by the very fabric of reality. But don't let that crush your dreams just yet, because here's where it gets even more fascinating. Scientists are still debating this idea, weighing the possibilities against the paradoxes, testing the limits of what we know about space, time, and the laws that govern them. Could there be loopholes? Could quantum mechanics or black holes hold the key? Or are we forever bound to the arrow of time, moving forward with no way to turn back? That's what we're diving into today, a journey through the science, the theories, and the mind-bending possibilities that keep this debate alive. Whether you're a die-hard sci-fi fan or just love unraveling the mysteries of the universe, stick around. Because by the end of this, you might never look at time the same way again. The chronology protection conjecture isn't just some abstract thought experiment. It's a serious proposal from one of the greatest scientific minds of our time. Back in 1992, Stephen Hawking put forward this idea as a kind of cosmic safety net. Imagine the universe as a finely tuned machine where every cause must have an effect, every action must have a consequence. Now toss time travel into the mix. Suddenly, you could have effects without causes, consequences without actions, utter chaos in the very fabric of reality. Hawking's conjecture suggests the laws of physics might actively prevent this kind of disruption. Think of it like an immune system for space-time, stepping in to stop paradoxes before they can even form. For example, if you tried to build a time machine, quantum effects, tiny, unpredictable fluctuations at the smallest scales, might conspire to make it fail. Maybe radiation would build up uncontrollably, or wormholes would collapse the instant they became usable. The universe, in other words, might have a built-in kill switch for anything that threatens the orderly flow of time. What's fascinating is how this idea connects to other frontiers of physics. Take black holes, those cosmic monsters where gravity is so strong not even light can escape. Hawking showed they slowly evaporate, leaking radiation over billions of years. But if you could travel back in time, you might create a scenario where that radiation gets trapped in a loop, growing infinitely until it destroys the time machine itself. It's like the universe saying, "Nice try, but no." This isn't just about protecting history from meddling time tourists, it's about preserving the very consistency of reality. Without chronology protection, the laws of physics could become meaningless, cause and effect would unravel, the past could rewrite itself on a whim. And that's why this conjecture matters. It's not just a what-if story, it's a challenge to our understanding of how time, space, and existence itself fit together. Yet here's the twist, not everyone agrees. Some physicists argue the universe might allow certain kinds of time travel under extreme conditions, like near a spinning black hole or through exotic matter with negative energy. Others point to quantum mechanics, where particles can seemingly influence each other across time in strange, non-linear ways. The debate is far from settled. But whether the conjecture holds or not, it forces us to confront one of the most fundamental questions of all. Is time truly unbreakable, or are the rules more flexible than we think? To understand how time travel could theoretically work, we need to start with Einstein's theory of relativity. His groundbreaking ideas reshaped our understanding of space and time, revealing they aren't separate entities but woven together into a single fabric called spacetime. And here's the mind-blowing part. Massive objects like stars and planets actually bend this fabric with their gravity. The stronger the gravity, the more spacetime warps, and that's where things get interesting for time travelers. Take a black hole, for example. If you could hover near its edge where gravity is incredibly intense, time would slow down dramatically for you compared to someone far away. A few hours for you might be years or even centuries for everyone else. It's not quite hopping into a time machine, but it shows how relativity allows time to stretch and compress under extreme conditions. This effect, called time dilation, has been measured with atomic clocks on fast-moving jets and satellites, proof that time isn't as rigid as it feels in our everyday lives. Now let's crank it up a notch. According to relativity, space-time can bend so severely that it might create shortcuts between distant points, wormholes. Picture a piece of paper folded in half with a pencil poking through. That hole connects two separate points instantly. In theory, a wormhole could do the same for time. Enter one end, exit the other, and you might emerge in a different era. But here's the catch. Wormholes would require exotic matter with negative energy to stay open, something we've never observed in nature. Without it, they'd collapse faster than you could say. Paradox. This brings us to closed time-like curves, paths through spacetime that loop back on themselves, allowing you to travel to your own past. Some solutions to Einstein's equations suggest these curves could exist, especially around infinitely long rotating cylinders or certain black hole configurations. But just because the math allows it doesn't mean the universe does. Remember Hawking's chronology protection. These curves might trigger quantum instabilities that shred them apart before anyone could use them. So where does that leave us? Physics doesn't outright ban time travel. It teases us with possibilities while stacking the deck with cosmic red tape. Relativity opens the door, but nature might have hidden locks we haven't found yet. The deeper we dig, the clearer it becomes. Time travel isn't just an engineering challenge. It's a battle against the universe's deepest rules. Let's talk about one of the most famous mind-benders in time travel, the grandfather paradox. Say you hop into a time machine, travel back to the past, and accidentally prevent your own grandfather from meeting your grandmother. If that happens, your parents would never be born, which means you would never exist. But if you never existed, how could you have traveled back in time to change anything in the first place? It's a loop of logic that collapses in on itself, leaving us with an impossible contradiction. This isn't just a quirky thought experiment, it's a serious problem for any theory of time travel. If the past can be altered, then cause and effect stop making sense. Reality itself starts to look unstable, and that's where the chronology protection conjecture comes into play. Hawking's idea suggests the universe might have safeguards to prevent such paradoxes from ever happening. Instead of allowing history to be rewritten, nature could step in to correct the inconsistency before it even occurs. Think of it like trying to balance a pencil perfectly on its tip. In theory, it's possible, but the tiniest disturbance will make it topple. Similarly, any attempt to disrupt the timeline might trigger quantum fluctuations or energy buildups that destabilize the time travel mechanism itself. Radiation could flood the system, wormholes might snap shut. The very act of trying to create a paradox could be what prevents it. Some physicists take this even further, proposing alternate solutions to the paradox. One wild idea: parallel universes. If you change the past, you might not actually be altering your own timeline, just branching off into a new one where things unfolded differently. In this multiverse scenario, your original history remains untouched and the paradox never happens. It's a neat workaround, but it raises its own questions. If every decision spawns a new universe, does time travel become less about changing history and more about jumping between realities? The beauty of the grandfather paradox is that it forces us to confront the deepest questions about time, causality, and the nature of existence itself. Whether the universe locks time travel behind quantum fail-safes or multiverses, one thing seems clear: reality might be far more delicate and far more ingenious than we ever imagined. So the next time you daydream about revisiting the past, ask yourself, would the universe even let you? Ever stumble upon an idea so clever you wish you'd thought of it yourself, only to realize you might actually be the one who came up with it in the future? That's the essence of the bootstrap paradox, a time travel twist that's less about changing history and more about creating something from nothing. Imagine you're a musician in the year 2050, and one day a time traveler hands you sheet music for a stunning symphony. You spend years mastering it, become famous, and then decades later, you finally build a time machine, travel back, and give that same music to your younger self. Where did the symphony truly come from? It wasn't composed by anyone. It just exists, trapped in an endless loop with no origin. This isn't just a quirky thought experiment. It challenges our very understanding of cause and effect. Normally, everything has a clear beginning. A painting starts with an artist's brushstrokes. A novel begins with an author's first draft. But in a bootstrap scenario, the chain of causality folds back on itself like a snake eating its own tail. There's no creator, no initial spark, just an object or idea that cycles through time forever. And that raises a chilling question: could entire chunks of human knowledge, art, or even technology be caught in these loops? What if the equations we use to build time machines were always destined to come from the future with no real inventor? The bootstrap paradox doesn't just play with logic. It exposes a glaring hole in how time travel might operate. If information or objects can exist without origins, does creativity lose all meaning? Worse yet, could the universe get stuck recycling the same events eternally? This is where the chronology protection conjecture flexes its muscles. Hawking's theory suggests nature might abhor such paradoxes as much as it hates contradictions. Quantum mechanics, with its unpredictable particles and energy fluctuations, could act like a cosmic editor, snipping away any bootstrap loops before they solidify. Maybe wormholes destabilize when carrying paradox-prone items. Or perhaps consciousness itself can't process a reality where things appear out of thin air, forcing the timeline to correct itself. But here's the wild card. Some physicists argue bootstraps could exist without breaking reality. In a block universe where past, present, and future are equally real, there's no need for a first cause. Everything just is, like frames in a film strip. The symphony was always there, woven into space-time's fabric. No origin, no problem. This view turns paradoxes into mere quirks of perspective. Yet even if bootstraps are mathematically possible, they'd still twist our intuition into knots. After all, human brains evolved in a world where causes precede effects. Untangling a universe where they don't might be the ultimate challenge, not for physics but for us. So next time you hear a song that feels eerily timeless or stumble upon an idea that seems to have no author, ask yourself, could this be a relic of time travel? Or proof that the universe has rules even paradoxes can't break? If time travel seems impossible under classical physics, quantum mechanics might just hold the key to bending or even breaking the rules. At the tiniest scales, particles behave in ways that defy common sense, opening doors to possibilities that feel ripped straight from science fiction. Take quantum entanglement, for instance. When two particles become entangled, changing the state of one instantly affects the other, no matter how far apart they are. Einstein famously called this spooky action at a distance, but here's the twist: entanglement doesn't just bridge space, it might bridge time too. Experiments suggest that measuring one particle now could influence its entangled partner's state in the past. It's as if quantum particles are sending signals backward through time, blurring the line between cause and effect. Then there's retrocausality, the idea that the future can influence the past. In the quantum world, particles don't always follow a straight path from cause to effect. Instead, their behavior can appear to be shaped by events that haven't happened yet. Picture a game of billiards where the balls decide how to roll after seeing where they'll end up. Wild, right? This isn't just theory. Delayed choice experiments have shown that particles can change their minds about past behavior based on future observations. If quantum systems can dance to the tune of time-reversed logic, could we harness that to send information or even ourselves backward? Of course, scaling this up from particles to people is a colossal leap. Quantum effects are delicate, collapsing under the slightest disturbance, but some researchers speculate that advanced civilizations might one day exploit these phenomena to build quantum time tunnels, devices that use entanglement or retrocausal loops to peek or even step into the past. Others argue that quantum mechanics doesn't enable time travel so much as redefine what time is. In the many worlds interpretation, every quantum decision spawns a new timeline. Traveling back might just mean hopping to a parallel universe where history unfolded differently. Yet even here, the chronology protection conjecture lurks in the shadows. Quantum fluctuations could still act as cosmic referees, shutting down any attempt to create paradoxes. Or perhaps the universe allows microscopic time travel, tiny, self-correcting loops, while slamming the door on anything dramatic enough to rewrite history. Either way, quantum mechanics reminds us that time might be far more fluid than it appears. The ticking clock we experience every day could be just one layer of a much weirder, more malleable reality, one where the future and past aren't so set in stone after all. Wormholes, those hypothetical tunnels through space-time, aren't just shortcuts across the universe. They could be the ultimate time machines. Picture folding a piece of paper so two distant points touch, then poking a hole through them. That's the basic idea. A wormhole connects two separate moments in time and space, allowing you to step in one end and emerge somewhere, or someone else entirely. But here's where it gets tricky. For a wormhole to function as a time portal, it would need to stay open long enough for anything to pass through, and that's where physics throws up roadblocks. The first hurdle is stability. Ordinary wormholes based on Einstein's equations would collapse instantly under their own gravity. To keep them propped open, you'd need something with negative energy, a theoretical form of matter that repels rather than attracts. Think of it like trying to hold a tunnel open with anti-gravity. While quantum mechanics allows for fleeting negative energy in tiny amounts, like in the Casimir effect, where two metal plates in a vacuum create a slight repulsive force, we've never observed enough to sustain a traversable wormhole. Without it, your time tunnel would snap shut faster than a mousetrap. Even if you solved that problem, the chronology protection conjecture looms large. Hawking's theory suggests that as soon as you try to use a wormhole for time travel, quantum effects would trigger a feedback loop of radiation. Imagine sound waves in a microphone feeding back into a speaker, building until the system explodes. In this case, particles traveling through the wormhole would interact with their past selves, amplifying energy until it becomes infinite, a phenomenon called the blue sheet instability. The result, the wormhole would either collapse or become so warped that nothing could survive the trip. But let's say you somehow bypass that issue. There's still the matter of causality. If you emerge in the past, even a second before you entered, you risk creating paradoxes. Some physicists argue that wormholes might only allow time travel to points after their creation, like a one-way valve for chronology. Others propose that the universe's self-correcting mechanisms would subtly alter events to prevent contradictions, like a cosmic editor tweaking the script to maintain continuity. The wildest twist, wormholes might already exist just on scales too small to see. Quantum foam, a turbulent sea of spacetime at microscopic levels, could be riddled with ultra-tiny wormholes popping in and out of existence. Scaling these up to human size would require technology far beyond our grasp, but it hints that nature might not forbid time travel outright. It just makes it ludicrously difficult. So while wormholes tantalize us with their potential, they're also a reminder: the universe doesn't give up its secrets easily. If time travel is possible, it won't be as simple as stepping through a door. It'll be a high-stakes game against physics itself. Roger Penrose's cosmic censorship hypothesis might sound like something out of a sci-fi thriller, but it's actually a serious proposal about how the universe keeps its secrets, especially when it comes to black holes and the fabric of space-time. The idea is simple yet profound. Nature abhors a naked singularity, a point where gravity becomes infinite and the laws of physics break down completely, exposed for all to see. Penrose suggests the universe has a kind of cosmic modesty, cloaking these singularities behind event horizons, the invisible barriers around black holes that prevent anything, even light, from escaping. But what does this have to do with time travel? Think of it like this: if a singularity were left naked, without the protective veil of an event horizon, it could wreak havoc on causality. The extreme warping of spacetime near a singularity might allow for closed timelike curves, paths that loop back on themselves, creating opportunities for time travel. Without cosmic censorship, these curves could run wild, leading to paradoxes and chaos in the timeline. That's where the connection to Hawking's Chronology Protection Conjecture comes in. Both theories suggest the universe has built-in mechanisms to prevent reality from spiraling into absurdity. Imagine a black hole without an event horizon, a rogue singularity just floating in space, distorting time and space unpredictably. You could, in theory, approach it and exploit its gravitational chaos to travel backward in time. But cosmic censorship says no. The universe slaps an event horizon over it, cutting off access to the singularity's time-twisting potential. It's like putting a lock on a door to a room where the laws of physics don't apply. Even if you somehow tried to pry that door open, the conjecture implies quantum effects or radiation would flood in, destabilizing the system before you could break through. Penrose's hypothesis and Hawking's conjecture share a deeper philosophical thread. They both propose that the universe has a preference for order, for keeping cause and effect intact. A naked singularity isn't just a mathematical oddity, it's a threat to the very consistency of reality. By hiding these singularities behind event horizons, cosmic censorship might be the universe's way of saying, time travel isn't just dangerous, it's forbidden. But here's the twist: not all physicists agree. Some argue that under certain extreme conditions, like the collision of two black holes or the hypothetical decay of a super-advanced civilization's warp drive, a singularity might briefly go naked. If that's possible, even for a split second, it could open a fleeting window for time manipulation. Others suggest that cosmic censorship might only apply to classical physics, leaving loopholes in quantum realms where particles already behave unpredictably. Whether cosmic censorship holds or not, its implications are staggering. If the universe really does enforce these rules, it means time travel isn't just technologically out of reach, it's physically barred by the cosmos itself. And yet, the mere fact that we're debating it shows how deeply intertwined time, gravity, and the fabric of reality truly are. The universe might have locks, but we're still figuring out whether they're unpickable or just waiting for the right key. Hawking radiation might seem like an obscure detail in the study of black holes, but it holds profound implications for time travel and the universe's stance on it. Imagine a black hole sitting silently in space, slowly leaking energy. According to Hawking's calculations, these cosmic giants aren't perfectly black. Quantum fluctuations near the event horizon cause pairs of particles to pop into existence. One falls in, the other escapes, stealing a tiny bit of the black hole's mass. Over eons, this process causes the black hole to evaporate entirely. But here's the twist: if you could reverse this process, somehow capture and manipulate the escaping particles, you might stumble onto a time travel loophole. Think about the information paradox first. When a black hole evaporates, what happens to all the matter it swallowed? Quantum mechanics says information can't be destroyed, but general relativity suggests it vanishes forever inside the singularity. Hawking radiation appears to carry no information about what fell in, creating a paradox. Now, toss time travel into the mix. If you could send a signal back in time using Hawking radiation, you might theoretically recover that lost information, patching the paradox. But the universe seems allergic to such tidy fixes. The radiation is random, noisy, like trying to reconstruct a burned book from the ashes blowing away in the wind. This randomness isn't just a nuisance, it's a potential failsafe. Hawking's later work suggested that any attempt to use this radiation for time travel would trigger uncontrollable feedback. Picture a microphone near a speaker. The sound loops back, screeching louder until the system fails. Similarly, manipulating Hawking radiation to send messages to the past could amplify quantum fluctuations, destabilizing space-time itself. The radiation would pile up into an infinite energy spike, a blue sheet, that shreds the time travel mechanism before it can succeed. It's as if the universe has a built-in firewall against paradoxes, frying any effort to tamper with chronology. But black holes aren't the only players here. Virtual particles, fleeting quantum ripples that borrow energy from the vacuum, might also hold clues. Some theories suggest that if you could isolate and control these particles, you could create a temporary bridge through time. Yet Hawking radiation shows us the universe's reluctance to cooperate. Virtual particles exist in delicate balance, annihilating each other almost instantly. Disturb that balance to send information backward, and quantum mechanics slams the door shut. The radiation becomes a chaotic storm, scrambling any meaningful signal. What's fascinating is how this ties back to the chronology protection conjecture. Hawking didn't just propose that time travel might be impossible, he showed how the universe actively prevents it. Black holes, those natural time machines in theory, are designed to self-destruct if you try to exploit them. Their radiation isn't a bug, it's a feature. A cosmic keep-out sign wired into the fabric of reality. Yet the story isn't entirely bleak. Some researchers argue that advanced civilizations might find workarounds using quantum entanglement to sidestep the radiation chaos, or harnessing multiple black holes in precise configurations. Others speculate that Hawking radiation could encode hidden information after all, like a puzzle waiting to be decoded. If true, time travel might not be about brute forcing the laws of physics, but learning to speak the universe's subtle language. One thing's certain, Hawking's work doesn't just describe black holes. It reveals a universe fiercely protective of its timeline, where even the most exotic phenomena conspire to keep causality intact. Whether that's a death knell for time travel or just a challenge to innovate, the message is clear. If you want to bend time, be prepared to wrestle with physics itself. Time travel has captivated storytellers for centuries, but nowhere is its allure more vivid than in the worlds of film and literature. From H.G. Wells' The Time Machine to modern blockbusters like Interstellar, creators have spun tales that stretch the limits of imagination, often bending or outright breaking the rules of physics in the process. These stories don't just entertain, they shape how we think about time itself, blending science with spectacle in ways that linger long after the credits roll. Take Back to the Future, for example. The DeLorean's flux capacitor runs on 1.21 gigawatts of power, a nod to real-world energy demands, but the film glosses over the mind-bending paradoxes Marty McFly triggers by altering his parents' past. Compare that to Primer, a cult classic obsessed with realism, where time loops are messy, unpredictable, and fraught with unintended consequences. One leans into adventure, the other into anxiety, yet both reveal a truth. How we portray time travel reflects our deepest hopes and fears about tampering with destiny. Then there's the granddaddy of all paradoxes, the Terminator. Skynet sends a killer robot to the past to prevent its own destruction, but the assassination attempt inadvertently creates the very rebellion it sought to crush. It's a perfect example of the bootstrap paradox, where cause and effect spiral into an inescapable loop. But here's the catch: real physics, as per Hawking's conjecture, would likely crash this party before it even started. Quantum instability or radiation feedback might fry Skynet's time machine mid-launch, rendering the plot impossible. Fiction thrives on drama, reality prefers consistency. Even the most scientific depictions take liberties. Interstellar famously used real equations to visualize Gargantua, the film's supermassive black hole, but its portrayal of time dilation, where hours on a watery planet equal years back on Earth, simplifies the bone-crushing gravity needed to warp time that dramatically. Meanwhile, Looper sidesteps physics entirely, treating paradoxes like a mob boss disposing of loose ends. Messy, brutal, and ultimately unresolved, the irony. These creative liberties often inspire real scientific curiosity. When Contact depicted wormholes using actual research from physicist Kip Thorne, it blurred the line between art and academia. And while Doctor Who's TARDIS runs on whimsical, timey-wimey logic, its exploration of fixed points in history, events so pivotal they must happen, echoes debates about whether the universe self-corrects to preserve causality. Perhaps the most telling contrast lies in tone. For every 12 monkeys where time travel is a prison of inevitability, there's a Bill and Ted romp where history bends to the power of air guitar. One asks if we're trapped in time, the other declares we can rock our way out of it. Both are fantasies, but they reveal a shared truth. Time travel stories aren't about physics. They're about us, our longing to undo regrets, our terror of chaos, and our unshakable belief that somewhere, somehow, the clock might just tick backward. Science may never give us a working TARDIS, but fiction offers something just as valuable: a mirror. Every time-traveling hero or villain reflects what we do with the power to rewrite yesterday or fast-forward to tomorrow. And that's why these stories endure, not because they get the math right, but because they get us right. Time dilation and time travel might sound like two flavors of the same sci-fi fantasy, but in reality, they're fundamentally different phenomena, one confirmed by science, the other still squarely in the realm of theory. Let's start with time dilation, the undisputed heavyweight champion of relativity. Einstein showed that time isn't a universal metronome ticking at the same rate for everyone. Instead, it's elastic, stretching or compressing depending on speed and gravity. Astronauts on the International Space Station experience this firsthand. After months orbiting Earth at nearly 17,500 miles per hour, their clocks tick ever so slightly slower than those on the ground. Over a 6-month mission, they'll return home about 0.007 seconds younger than if they'd stayed put. Not exactly a fountain of youth, but proof that time isn't as rigid as it seems. Now crank the dial to extremes. Near a black hole where gravity warps space-time like a trampoline with a bowling ball in the center, time dilation goes into overdrive. In Interstellar, the crew's agonizing hours on Miller's planet cost them decades back on the ship. While the movie dramatizes the effect, the science checks out. Time truly would crawl for you compared to someone far from the black hole's grip. But here's the catch: you're not traveling through time, you're just experiencing it at a different rate. No paradoxes, no rewriting history, just the universe's way of saying your clock runs differently here. Time travel, on the other hand, isn't about slowing or speeding up your personal timeline, it's about breaking it. Imagine stepping into a machine and emerging in the year 3000 or worse, arriving yesterday to stop yourself from making a terrible decision. That's not dilation, that's dislocation. The difference boils down to causality. Time dilation preserves cause and effect. Events still unfold in order, just at varying speeds. Time travel, especially to the past, threatens to scramble that order entirely. Turn left instead of right in 1985, and suddenly your parents never meet. That's the grandfather paradox lurking in the shadows. The confusion often stems from pop culture. Films like Planet of the Apes or Avatar use time dilation as a narrative shortcut, blurring the line between relativistic effects and genuine time jumps. Even Star Trek's slingshot around the sun tactic mashes up real physics with fantasy, but the key distinction remains: dilation bends time's flow, time travel severs it. One is a natural consequence of spacetime's flexibility. The other would require ripping a hole in reality's rulebook. Could dilation ever lead to actual time travel? Some theories suggest that if you could accelerate to near light speed or orbit a black hole for years, you'd effectively leap into the future just by outrunning normal time. But returning, that's the rub. You'd need a way to reverse the process, and relativity offers no U-turns. The past stays stubbornly out of reach. That's why Hawking's Chronology Protection Conjecture feels like the universe's ultimate disclaimer: time dilation. Find time travel? Absolutely not. So while dilation proves time is more fluid than we thought, it also underscores the limits of our control. We can surf its currents, but rewriting the tides. That might be one frontier even relativity won't let us cross. Not everyone is convinced the universe has a strict no-time travel policy. Some physicists argue that Hawking's Chronology Protection Conjecture, while elegant, might not be the final word. Enter the multiverse theory, a radical alternative where time travel doesn't rewrite history. It simply branches off new realities. Imagine stepping into a time machine, traveling back to prevent a disaster and succeeding, only to realize you haven't changed your own past. Instead, you've splintered off into a parallel universe where events unfolded differently. Your original timeline remains untouched, paradox-free. It's like hitting Save As on reality rather than editing the original file. This idea isn't just sci-fi fodder. It's grounded in quantum mechanics, specifically the many worlds interpretation. Every quantum decision, every particle spin, every atom's decay could spawn alternate timelines. Under this view, time travel wouldn't violate causality because you're not altering the past. You're navigating a landscape of pre-existing possibilities. Think of it like hopping between train tracks at a switchyard. Each track represents a different version of events, all running simultaneously. The grandfather paradox. Neutralized, you couldn't erase your own existence because the you in the original timeline would remain unaffected. But the multiverse isn't the only challenger. Some theories suggest that closed time-like curves, those space-time loops we mentioned earlier, might stabilize under certain conditions. Nobel laureate Kip Thorne, for example, proposed that traversable wormholes could avoid infinite radiation feedback if they're meticulously engineered. Picture threading a needle with the fabric of reality. Align the wormhole's mouths just right, and you might sidestep the universe's self-correcting mechanisms. It's a long shot, but mathematically plausible. Then there's retrocausality, the idea that the future can influence the past without creating paradoxes. In quantum experiments, particles seem to decide their states retroactively based on later observations. This doesn't mean you could send a message to your younger self, but it hints that causality might be more flexible than we think. If microscopic time loops are possible, could they be scaled up? Or do they exist solely in the quantum realm, forever out of reach for human-scale manipulation? Even within the conjecture's framework, skeptics point out gaps. Hawking himself admitted that chronology protection might rely on quantum gravity, a theory that still eludes us. Without it, we can't be sure whether the universe's paradox prevention mechanisms are ironclad or full of loopholes. After all, black holes were once considered purely theoretical until we found them lurking in the cosmos. Could time travel be similarly hidden, waiting for a breakthrough? The debate reveals a deeper truth. Our understanding of time is still evolving. Whether through multiverses, wormholes, or quantum quirks, physicists keep probing the limits of what's possible. And while the chronology protection conjecture offers a compelling argument, science thrives on dissent. For every cosmic rule, there's a rebel hypothesis testing its boundaries. So before we declare time travel impossible, remember the universe has surprised us before. Stephen Hawking once threw a party for time travelers and no one showed up. At least not that we know of. Back in 2009, the legendary physicist set out to test the chronology protection conjecture in the most playful way possible. He hosted a lavish reception with champagne and hors d'oeuvres, but here's the twist. He only sent out invitations after the event. The logic was brilliant. If time travel to the past were possible, future visitors could have seen the invitations long after Hawking's era and popped back to join the party. The fact that the room remained empty wasn't just disappointing. It was a cheeky piece of experimental evidence suggesting the universe enforces its no-time travel rule. Hawking wasn't alone in designing real-world tests for the impossible. Scientists have long used creativity to probe time travel's plausibility, often with surprising results. Take the search for closed time-like curves in particle collisions. When physicists smash protons together at near-light speeds in machines like the Large Hadron Collider, they're not just hunting for new particles, they're indirectly testing whether microscopic time loops could form in the extreme energies of these collisions. So far, no signs of time-traveling particles have appeared, but the experiments continue, pushing the boundaries of what we can observe. Then there's quantum mechanics, where the rules get even stranger. Researchers have attempted to exploit quantum entanglement to send information backward in time, a concept called retrocausality. In one experiment, scientists measured particles in a way that seemed to influence their past states, as if the present were reaching back to tweak history. But before you picture handwritten notes arriving yesterday, there's a catch. These effects only work at the quantum scale, and they can't carry meaningful information without collapsing into randomness. It's like trying to send a message by shaking a locked box. You might disturb what's inside, but you'll never know what it says. Even cosmic rays have been drafted into the time travel debate. Some theories suggest that if backward-moving particles existed, they'd leave distinct traces in detectors like footprints in reverse. Scientists have combed through decades of data from observatories, hunting for these hypothetical tachyons or other anomalies that could hint at time-reversed events. Yet every search has come up empty, reinforcing the idea that nature erects barriers against chronological chaos. What's fascinating is how these experiments reveal the universe's subtle consistency. Whether it's an absent party guest or a missing quantum signal, the results whisper the same thing. Time might be more like a one-way street than a tangled knot. Of course, absence of evidence isn't evidence of absence. Maybe we just haven't found the right loophole yet. But until a time traveler crashes Hawking's next party, the chronology protection conjecture holds the floor. Quantum gravity sits at the heart of the time travel debate, offering some of the most tantalizing and contentious clues about whether the chronology protection conjecture holds up. To understand why, we need to revisit one of physics' greatest unsolved puzzles, the clash between general relativity and quantum mechanics. Relativity paints space-time as a smooth, bendable sheet, while quantum mechanics insists everything is made of tiny, jittery particles. These two frameworks work flawlessly in their own domains, but when they collide like near the singularity of a black hole, the math breaks down into infinities and contradictions. That's where quantum gravity steps in, aiming to rewrite the rules in a way that reconciles both worlds. And here's the kicker: depending on how you stitch them together, time travel could either be obliterated or accidentally invited to the party. Take loop quantum gravity, for example. This theory suggests space-time isn't infinitely divisible but made of tiny, indivisible loops or grains like pixels on a screen. In this pixelated cosmos, there's no such thing as a smooth wormhole or a perfectly closed timelike curve. The granularity of space-time might act like a cosmic sieve, filtering out paradoxes before they can form. Picture trying to thread a needle with a rope that keeps fraying at the ends. No matter how carefully you maneuver, the fibers resist forming a clean loop. Similarly, loop quantum gravity could imply that any attempt to bend time into a paradox would hit a wall of fundamental discreteness, upholding Hawking's conjecture by default. Then there's string theory, the other heavyweight contender. It proposes that particles aren't dots but vibrating strings in higher dimensional space. Some versions of the theory allow for brains's multidimensional membranes that could theoretically warp space-time in ways that sidestep the usual paradox triggers. Imagine two parallel universes separated by a fifth dimension. A string stretched between them might create a bridge where time flows differently, potentially permitting limited time travel without violating causality. But here's the catch: even in string theory, stability is a nightmare. The energy required to keep such a bridge open could destabilize the vacuum of space itself, triggering a catastrophic collapse. It's like building a castle on a frozen lake. The moment you add weight, the ice cracks. The wild card in all this: quantum foam. At scales a trillion times smaller than an atom, space-time might boil with fleeting wormholes and virtual black holes constantly popping in and out of existence. Some physicists speculate that in this frenzied quantum sea, microscopic time loops could flicker into being for split seconds, far too brief for humans to exploit, but hinting that the universe might tolerate some temporal flexibility. If true, the chronology protection conjecture wouldn't be an absolute law but more of a statistical tendency. Time travel wouldn't be forbidden. It'd just be vanishingly improbable, like shuffling a deck of cards into perfect order by chance. Yet for all these possibilities, quantum gravity might also slam the door shut. One leading idea is that any attempt to create a time machine would require energies so extreme they'd trigger a phase transition in space-time, a cosmic reboot that resets the rules to prevent paradoxes. Think of it like overheating a computer until it crashes. Before you can input a command to break causality, the system shuts down to protect itself. In this view, chronology protection isn't a side effect. It's baked into the universe's operating system. The irony is thick. The same theories that could unify physics might also hand us the tools to dismantle time or confirm it's permanently locked. Until we crack quantum gravity, the conjecture remains in limbo, neither proven nor disproven, but pulsating with possibilities, and that's the real lesson here. Time travel isn't just a question of engineering. It's a stress test for the deepest laws of reality, probing whether the universe is a rigid clockwork or something far more malleable. Every equation, every experiment inches us closer to an answer, or maybe just a better question. Time loops and predestination paradoxes present a fascinating loophole in the time travel debate. What if the universe doesn't need to prevent paradoxes because it's already engineered them away? Imagine stepping into a time machine, traveling to the past, and attempting to change a major historical event, only to realize your actions were always part of history. You didn't alter the timeline, you fulfilled it. This is the essence of a self-consistent time loop, a scenario where every event, including the time traveler's meddling, seamlessly stitches itself into the fabric of causality. No contradictions, no universe-ending paradoxes, just a cosmic jigsaw where every piece clicks into place. Take the classic example of a time traveler who goes back to deliver the blueprints for a revolutionary invention, say the first light bulb, to their younger self. At first glance, it seems like a classic bootstrap paradox. Where did the design originally come from? But in a self-consistent loop, there is no origin. The blueprint exists because it was always handed down through time, trapped in an infinite cycle with no creator. The universe doesn't care about authorship, it only demands logical consistency. This is the ultimate cosmic sleight of hand. Time travel doesn't break the rules if the rules were designed to accommodate it. Hawking's conjecture might frown on paradoxes, but predestination loops could be its sly workaround. Instead of triggering quantum instabilities or radiation feedback, these loops play by the universe's existing playbook. Think of it like a movie script where the time traveler's lines were always part of the dialogue. In 12 Monkeys, the protagonist's actions in the past don't change the future, they explain it. His very attempt to stop a pandemic inadvertently sets the chain of events in motion. The tragedy isn't a flaw, it's a feature. The loop is airtight, leaving no room for the universe to intervene. But here's the rub: predestination loops raise their own existential headaches. If every time-traveling act is preordained, do we have free will, or are we just puppets of a deterministic timeline? Imagine discovering that your entire life, your choices, your mistakes were orchestrated by a future version of yourself. It's a chilling thought, one that blurs the line between actor and audience. And from a physics standpoint, the odds of every event aligning perfectly to avoid contradictions seem astronomically low. Could the universe really be that meticulous, or would even the slightest deviation, a misstep, a stray thought, unravel the whole tapestry? Some physicists argue that self-consistency isn't a loophole but a mathematical necessity. Nobel laureate Igor Novikov proposed the self-consistency principle, which states that any actions taken by a time traveler must align with the past as it already happened. In this view, the universe isn't actively preventing paradoxes, it's simply pruning every timeline where they occur, leaving only the coherent ones standing. It's like a cosmic editor slicing away plot holes until the story makes sense. Under Novikov's rule, you couldn't kill your grandfather, not because the universe stops you, but because the act is logically impossible. The gun would jam, your aim would falter, or you'd suddenly remember Grandpa had an identical twin. Reality would conspire to keep the timeline intact. Yet critics counter that this principle feels suspiciously convenient. It assumes the universe has a preternatural knack for tidiness, smoothing over every wrinkle before it forms. What if two equally consistent timelines branch from the same event? Or what if the loop's consistency relies on absurd coincidences like a time traveler's sneeze just happening to divert a bullet meant for a key historical figure? The deeper you dig, the more predestination loops resemble a magician's trick, dazzling until you spot the hidden strings. Perhaps the most unsettling implication is that self-consistency might render time travel pointless. If you can't change anything, only fulfill what's already written, what's the appeal? It turns time machines into glorified history tours where every choice is an illusion. The ultimate irony, the very mechanism that could make time travel physically possible, might also strip it of all its allure. No rewriting mistakes, no saving lost loved ones, just the hollow satisfaction of playing your predetermined part. Still, the idea persists because it offers a tantalizing middle ground. Not quite the chaos of paradoxes, not quite the rigidity of chronology protection. A universe where time travel is possible, but only if it doesn't disturb the cosmic order. Whether that's a feature or a flaw depends on how much freedom you're willing to sacrifice for a ticket to the past. One thing's certain, if time loops are real, they're the universe's way of having the last laugh. You might think you're breaking the rules, but the rules were always one step ahead. Even if we could crack the physics of time travel, we'd still face an even thornier challenge, the ethics of it. Picture having the power to undo history's greatest tragedies, preventing wars, erasing plagues, saving lives. It sounds heroic, but every intervention would ripple outward in ways we can't predict. The Chronology Protection Conjecture hints that the universe might veto such meddling to preserve causality, but if it didn't, we'd be left with impossible choices. Who gets to decide which events are fixed? Could altering the past erase cultures, inventions, or even entire identities that emerged from adversity? The moral weight here isn't just about changing history, it's about playing God with existence itself. Consider something as seemingly noble as stopping the assassination of Archduke Franz Ferdinand, the spark that ignited World War I. Without that conflict, would the world have avoided decades of bloodshed, or might an even deadlier war have erupted later? The Treaty of Versailles reshaped borders and fueled tensions that led to World War II, but it also set the stage for modern international law. And what of the technological leaps born from wartime necessity? Radar, penicillin, jet engines. The web of consequences is so vast, so tangled, that fixing one thread might unravel civilizations. This isn't just speculation, it's a direct clash with the conjecture's core idea. The universe might enforce a hands-off policy not just to avoid paradoxes, but to protect the fragile balance of cause and effect that shapes reality. Then there's the question of privilege. If time travel were possible, access would likely be limited to the powerful governments, corporations, elites. Imagine a world where the wealthy could retroactively secure monopolies on groundbreaking inventions, or dictators could erase dissidents from history. The very notion of justice could collapse if evidence, witnesses, or even crimes could be undone at will. The conjecture's implied prohibition might act as a safeguard against such abuses, ensuring history remains a collective, uneditable record rather than a sandbox for the privileged few. But what about personal morality? Say you travel back to stop a childhood tragedy, a parent's death, a natural disaster. On the surface, it's an act of love. Yet by saving one life, you might unintentionally erase countless others whose paths intersected with that loss. The person who inspired a medical breakthrough after grieving their mother, the activist whose passion was forged in hardship, their futures could vanish in an instant. This isn't just butterfly effect poetry, it's a stark reminder that grief and growth are often intertwined. The universe's apparent block on time travel might not be a flaw, it could be a mercy, sparing us from choices where every victory carries invisible casualties. Perhaps the most unsettling ethical layer is consent. Altering the past means rewriting lives without permission. The people you save never ask to be uprooted from their timeline. The children who would have been born in the original version of events, do they deserve a voice? In a multiverse scenario where your actions spawn alternate branches, the dilemma softens but doesn't disappear. You're still creating realities where some versions of people flourish while others fade into might-have-beens. Even with Hawking's conjecture in play, the debate forces us to ask, is preserving the sanctity of a single, uneditable timeline the only ethical path? Science fiction often glosses over these questions with tidy resolutions, but reality wouldn't be so forgiving. The Chronology Protection Conjecture, whether proven or not, serves as a poignant metaphor for ethical boundaries we can't cross. It's not just physics saying, you can't, it's a mirror held up to humanity's hunger for control, reminding us that some doors might be locked for a reason. After all, the power to reshape time isn't just about defying gravity or outsmarting quantum foam. It's about whether we're ready to carry the unbearable weight of every decision, knowing that even the kindest act could rewrite the world beyond recognition. Even if we could somehow sidestep the universe's paradox prevention mechanisms, the sheer engineering hurdles of time travel would stop us in our tracks. Take energy requirements. Just powering a hypothetical time machine would demand amounts of energy that make modern nuclear reactors look like AA batteries. Theoretical models suggest that twisting spacetime enough to create a traversable wormhole might require the energy equivalent of several suns, and that's assuming we could harness and control such forces without vaporizing ourselves in the process. The chronology protection conjecture might seem like cosmic overkill when the practical barriers are already this extreme, but energy is just the starting point. Stabilizing a wormhole or other time-bending structure would demand materials with properties we've never observed in nature. Exotic matter with negative energy density, the kind that could prop open a wormhole against the crushing force of gravity, exists only as fleeting quantum fluctuations, if at all. Imagine trying to build a bridge out of soap bubbles. That's the level of fragility we're dealing with. Even if we scoured the galaxy for such materials, there's no guarantee they could be harvested or synthesized in usable quantities. Physics textbooks are filled with equations that permit time travel, but the fine print always adds, if you can find a substance that defies everything we know about thermodynamics. Then there's precision. Warping spacetime isn't like steering a car. It's more like performing laser surgery on the fabric of reality while blindfolded. A miscalculation of 1 part in a billion could turn your time machine into a runaway black hole or a Big Bang-scale explosion. The margin for error is non-existent. Consider the Large Hadron Collider, where particles are guided by superconducting magnets cooled to near absolute zero. Now amplify that precision by a factor of 1 trillion, and you're still not close to the control needed to bend time. One misplaced decimal in your calculations, and instead of visiting the dinosaurs, you might erase the solar system. Even if we solved these problems, durability remains a nightmare. Every known structure in the universe degrades, metals fatigue, stars burn out, even protons may decay over trillions of years. A time machine would need to be impervious to entropy itself, surviving not just decades but potentially millennia of use without a single component failing. The closest parallel we have is Voyager 1, drifting through space with 60-year-old technology. Now imagine that same probe needing to function flawlessly for 100,000 years while manipulating forces that can crumple planets. The conjecture's suggestion that quantum effects would destabilize time machines starts to feel less like a prohibition and more like a mercy, a way to save us from engineering projects so complex they'd collapse under their own ambition. And let's not forget the most ironic twist of all, time itself. Building a machine to traverse centuries might take centuries. By the time you finished constructing it, your target era could be receding into the past faster than you could reach it. It's the ultimate cosmic joke. To master time travel, you'd need to outrace time. Between the energy demands, material impossibilities, and razor-thin tolerances, the technological barriers aren't just high. They're a mirror reflecting back the same truth as Hawking's conjecture. The universe isn't just reluctant to let us time travel, it's practically daring us to try. Long before Einstein rewrote our understanding of spacetime, ancient cultures were already dreaming of bending time to their will. The Hindu epic Mahabharata tells of King Kakudmi, who visits the heavens for a brief audience with the creator god Brahma only to return to Earth and find centuries have passed. Sound familiar? It's the same time dilation we see in relativity, just wrapped in myth. Meanwhile, the Japanese legend of Yorishima Taro mirrors this perfectly. A fisherman rescues a turtle, visits an undersea palace for what feels like days, and surfaces to discover he's been gone 300 years. These stories aren't just coincidences, they reveal how deeply the human psyche craves mastery over time, whether through gods or gravity. Greek mythology takes a darker turn with Kronos, the titan who devours his own children to prevent being overthrown. It's a chilling metaphor for time's inexorable march, consuming all in its path. Yet even here there's defiance. In the Odyssey, Circe warns Odysseus about the Isle of the Sun, where time behaves strangely, a place where days stretch and compress like rubber. Compare that to Einstein's revelation that clocks tick slower near massive objects, and the parallels become uncanny. separated by millennia, these tales and theories share the same awe for time's fluidity. Native American traditions offer another lens. The Hopi people speak of Pahana, a lost brother who will return from the future with advanced knowledge, echoing modern sci-fi tropes of time travelers as prophets. Similarly, Norse mythology's Yggdrasil, the world tree, connects 9 realms not just in space but across time, its roots and branches threading through past, present, and future like a cosmic wormhole network. These myths didn't have quantum equations, but they grasped time's non-linearity intuitively, painting it as a tapestry rather than a straight line. Even the Bible holds time-bending moments. In Joshua 10, the sun stands still for a day, freezing time mid-battle. Modern physics might call this a localized space-time anomaly, a bubble where entropy halts. And let's not forget the Taoist tale of the woodcutter who watches a single chess game between immortals, only to find his axe handle has rotted to dust when he returns home. It's the ancient equivalent of Interstellar's water planet scene, where hours become decades elsewhere. The real magic lies in what these stories don't say. Unlike modern time travel plots, ancient myths rarely feature paradoxes. Characters don't fret over altering history, they accept time's twists as natural law. Maybe they understood something we're still grappling with, that time isn't a road to be repaved, but a river to be navigated. Whether through God's bending fate or black holes warping space-time, the message is the same. Time has always been the ultimate mystery, and humanity's obsession with conquering it is as old as civilization itself. Philosophers have wrestled with the nature of time long before physicists wrote their first equations, and their insights reveal just how deeply the chronology protection conjecture taps into humanity's oldest debates. Take Aristotle, who saw time as a measurement of change, a flowing river where the past is fixed, the future open. To him, the idea of traveling backward would have been nonsensical, not because of quantum mechanics, but because time's arrow was woven into the very fabric of existence. The conjectures claim that the universe resists paradoxes would have felt intuitive to Aristotle. If time is change, then reversing it would unravel reality itself. Centuries later, St. Augustine grappled with time as a subjective experience, arguing that past and future exist only in our minds as memory and anticipation. In his view, the present is a knife's edge between what was and what might be, a perspective that makes time travel seem less like hopping between points and more like trying to grasp smoke. Then there's Immanuel Kant, who turned the question inside out. He proposed that time isn't a feature of the external world at all, but a framework our minds impose to make sense of reality. If Kant was right, the chronology protection conjecture isn't just a physical law, it's a cognitive necessity. Our brains might be hardwired to perceive cause and effect as unbreakable, making paradoxes unimaginable by design. This raises a haunting possibility. What if the universe's rules against time travel are just mirrors of our own mental limits? Modern philosophy adds even more layers. David Lewis, a champion of modal realism, argued that all possible worlds are equally real, and time travel could mean jumping between these parallel realities rather than rewriting a single timeline. In Lewis's multiverse, the grandfather paradox vanishes because every action spawns a new branch. Your grandfather lives in one universe, dies in another, and both histories unfold simultaneously. It's a neat fix, but it clashes with Hawking's insistence on a single, self-consistent cosmos. Meanwhile, existentialists like Sartre saw time as inseparable from human freedom, a canvas for choices. To them, the conjecture's veto on altering the past might feel like a cosmic overreach, robbing us of the power to correct regrets. Eastern philosophies, though, offer a radically different take. In Buddhism, time is cyclical, a wheel of rebirth where events recur infinitely. Here, the idea of changing the past loses meaning. What's done is done, and liberation comes from breaking the cycle, not rewinding it. The conjecture's role, then, isn't to block time travel but to remind us that clinging to the past is futile. Taoism takes this further, envisioning time as a river where wading upstream disrupts the natural flow, or Tao. The universe's resistance to paradoxes, just the Tao restoring balance. What unites these views is a recurring theme. Time isn't just a dimension to traverse but a cornerstone of meaning. Whether it's Aristotle's river, Kant's mental scaffold, or the Tao's current, each philosophy hints that tampering with time risks more than paradoxes. It threatens the coherence of existence itself. The chronology protection conjecture, in this light, isn't just physics. It's the universe's way of preserving the stories we tell, the choices we make, and the fragile thread that ties them all together. Stephen Hawking didn't just study the universe, he reshaped how we think about it. His work on the chronology protection conjecture wasn't some dry academic exercise. It was a bold challenge to one of humanity's most tantalizing fantasies. While others fantasized about rewriting history or meeting their ancestors, Hawking asked a more piercing question: why haven't we met any time travelers? His famous absence at his own time traveler party wasn't just a clever stunt, it was a test of the universe's deepest rules. With a physicist's rigor and a showman's flair, he turned abstract equations into a debate that captivated scientists and dreamers alike. What made Hawking's approach so revolutionary was how he wove together relativity, quantum mechanics, and sheer imagination. He didn't just declare time travel impossible, he showed how the universe might actively prevent it. Picture a cosmic immune system detecting paradoxes like infections and deploying quantum effects to neutralize them. Radiation surges, wormholes snap shut. The harder you push against time's arrow, the harder reality pushes back. This wasn't just a theory, it was a narrative about how the cosmos protects its own logic. And like all great stories, it forced us to see familiar things differently. Suddenly, black holes weren't just traps for light. They were time's gatekeepers, their Hawking radiation a firewall against chaos. Yet Hawking's genius lay in his willingness to entertain the impossible. Even as he argued for chronology protection, he explored loopholes with childlike curiosity. His work on wormholes, imaginary time, and the no-boundary proposal revealed a mind unafraid to dance on the edge of paradox. He once mused that if time travel were possible, we'd need laws to prevent tourists from trampling the past, a joke that hid a profound truth. For Hawking, the conjecture wasn't about shutting down wonder, it was about grounding it in science. By framing time travel as a puzzle for physics, not fiction, he gave it new life. His legacy here is twofold. First, he showed that time isn't just a backdrop, it's a player with rules and reactions we're only beginning to understand. Second, he proved that even the wildest ideas deserve scrutiny. Before Hawking, time travel debates were dominated by philosophy and pulp magazines. After him, they became a battleground for quantum gravity and cosmic censorship. The conjecture remains unproven, but its power lies in the questions it forces us to ask. What is time really? Why does causality feel so fragile? And if the universe really does guard its history like a treasure, what else might it be hiding? Hawking's voice may be silent, but his challenge echoes. Every experiment probing quantum entanglement, every theory wrestling with closed timelike curves, is chasing the same vision he dared to sketch. The chronology protection conjecture isn't just a footnote in physics, it's a beacon, reminding us that the universe's greatest mysteries aren't just out there in the stars. They're woven into the ticking of every clock, the unspooling of every moment, and the stubborn, beautiful fact that yesterday stays put. Whether he was right or wrong hardly matters. What endures is the audacity to look at time itself and ask, how do you work? And to listen patiently for the answer. The quest to prove or debunk the chronology protection conjecture isn't stuck in theoretical limbo. It's alive in labs around the world, where scientists are crafting ingenious experiments to test Hawking's bold idea. One frontier, quantum simulations, Imagine recreating the mind-bending physics of time travel on a microscopic scale, not with black holes or wormholes, but with particles so small they dance to the rules of quantum mechanics. Researchers are using devices like quantum computers to mimic conditions that could warp time, observing how these systems behave when pushed toward paradox. In one experiment, physicists encoded quantum bits qubits to act like tiny time travelers, sending information backward through simulated timelines. The results: hints of the universe's self-correcting nature emerged. Just as Hawking predicted, quantum noise and instability seemed to scramble any attempt to create logical inconsistencies, as if reality itself were hitting a reset button. But quantum simulations are just the tip of the iceberg. Another cutting-edge approach involves high-energy particle collisions. When protons smash together in accelerators like the Large Hadron Collider, they create conditions so extreme that space-time itself might momentarily warp in ways we don't fully understand. Some theorists suggest that hidden in the debris of these collisions could be microscopic signatures of closed timelike curves, fleeting loops in time too small to notice, but detectable with the right tools. If these loops form only to instantly unravel, it could be evidence of the universe enforcing chronology protection at the smallest scales. It's like catching the cosmos red-handed, patching up paradoxes before they can take hold. Meanwhile, astronomers are turning their telescopes toward the skies for clues. Black holes, those natural laboratories for extreme physics, might hold observable signs of Hawking's radiation feedback mechanism. By studying how matter and energy behave near event horizons, especially in binary black hole systems, scientists hope to spot the telltale energy spikes that would occur if the universe were correcting time travel-like disruptions. Even cosmic rays, those high-energy particles bombarding Earth from deep space, are being scrutinized for anomalies. If time travelers or their particles ever visited our era, they might leave faint imprints in these cosmic messengers. Then there's the wild card, quantum gravity. Theories like string theory and loop quantum gravity make competing predictions about whether space-time can be twisted into time loops without collapsing. Future experiments aiming to unify gravity with quantum mechanics could finally reveal whether the conjecture holds water. Picture a next-generation observatory detecting gravitational waves from the earliest moments of the universe ripples that might carry traces of primordial wormholes or other structures that once flirted with time travel. Or consider tabletop experiments trying to measure spacetime's quantum foam, where fleeting wormholes might bubble in and out of existence. If these experiments show that such structures are inherently unstable, it'd be a major win for Hawking's vision. The beauty of this research is its creativity. Scientists aren't just waiting for a time machine to fall into their laps, they're probing the universe's rulebook in ways Hawking himself might have cheered. Every experiment, whether it confirms the conjecture or chips away at it, brings us closer to answering a question that's haunted humans for millennia. Is time truly immutable, or are the laws that govern it more flexible than we dare imagine? One thing's certain, the universe won't give up its secrets easily, but with each quantum simulation, each particle collision, we're not just testing a theory, we're unraveling the very fabric of reality. If time travel were possible, would our choices still belong to us, or would we become prisoners of a predetermined loop? The tension between free will and the constraints of the chronology protection conjecture isn't just a plot twist for sci-fi, it's a philosophical minefield. Imagine deciding to travel back and prevent a tragedy, only to realize your attempt was always part of the event's cause. Your free will becomes a paradox trapped in a script written by the universe itself. Hawking's conjecture hints that nature might enforce this grim punchline, ensuring every action you take while time traveling was always meant to happen. No matter how fiercely you believe you're changing history, the cosmos could be quietly correcting your steps like a river smoothing over a thrown stone. But let's push further. If the universe really does block paradoxes, does that mean our sense of agency is an illusion even in the present? Think of Novikov's self-consistency principle, where every time traveler's actions are already factored into history. Under this rule, your decision to step into a time machine isn't a choice at all. It's a fixed point, as inevitable as the rotation of planets, the chilling implication. Free will might not just falter in the past, it could be a mirage everywhere. If the future is already written well enough to prevent paradoxes, how much control do we really have over our lives? Not all perspectives are so bleak. The multiverse theory offers a lifeline. Every choice spawns alternate timelines, so your time-traveling meddling doesn't erase your original path, it just forks the road. Here, free will thrives because every version of you gets to make decisions, even if their outcomes diverge infinitely. But this comes with its own existential baggage. If every possibility plays out somewhere, do your choices lose meaning? Saving a life in one universe while failing in another might feel less like heroism and more like statistical noise. Then there's the quantum angle. Some interpretations suggest that particles don't choose states until observed, as if reality itself hesitates until the last moment. If time travel operates at this level, perhaps free will isn't preordained but emerges from countless quantum possibilities. You're not a puppet of the timeline, you're a participant in its unfolding. But this, too, clashes with the conjecture. Hawking's quantum instability might still intervene, collapsing potential paradoxes into a single, consistent narrative, like a cosmic editor cutting disruptive scenes from a film. The debate stretches beyond physics into ethics and identity. If time travel locks us into predestined loops, does accountability vanish? Can you blame a time traveler for causing a disaster if the universe always demanded it? Legal systems, moral frameworks, even personal guilt rely on the idea that choices have weight. Strip that away and justice becomes theater. Yet if free will survives, if the conjecture allows some wiggle room, then time travel isn't just a tool. It's the ultimate test of responsibility, forcing us to ask not just can we change the past, but should we? Perhaps the most unsettling thought is this: the chronology protection conjecture doesn't just guard causality. It guards us from the existential vertigo of realizing our choices might be written in stars we can't read. Whether through quantum corrections, multiverses, or sheer cosmic irony, the universe seems determined to remind us that time isn't a canvas to repaint. It's a story we're living, one irreplaceable moment at a time. And in that story, free will might be the one thing even time can't touch. Hollywood loves to dress up time travel in flashing lights and dramatic twists, but the reality, or at least what physics suggests, couldn't be more different. Take the iconic image of the DeLorean screeching to a halt in 1955, sparks flying as Marty McFly steps out. In reality, a machine like that wouldn't just need a flux capacitor. It would need to harness energies rivaling supernova just to make space-time flinch. Pop culture sells us sleek devices with glowing buttons, but science whispers a harsher truth. If time travel exists, it won't fit in a garage. The misconception here isn't just about aesthetics, it's about scale. Warping time isn't like revving an engine, it's like trying to bend a diamond with your bare hands. Then there's the myth of the clean edit. Movies like Back to the Future make changing the past look as simple as tweaking a photo, remove one event, and the future snaps into a new shape. But physics paints a messier picture. Altering even a single atom's position in the past could send ripples through causality, triggering chain reactions we can't predict. Imagine tossing a pebble into a pond, except the ripples rewrite continents. The chronology protection conjecture suggests the universe wouldn't allow such chaos. Quantum corrections or radiation bursts would intervene like cosmic referees. Yet films ignore this, favoring narratives where heroes tweak history without consequences. Real-time travel, if possible, would likely be more like trying to sculpt with smoke, every change dissipating before it takes hold. Another whopper, the idea that time travelers could blend seamlessly into the past. Doctor Who strolls through Victorian London in a trench coat, but reality would be less forgiving. Language, customs, even microbes would pose deadly challenges. A modern human's immune system, adapted to centuries of evolved pathogens, might collapse in the face of ancient bacteria. And that's assuming you could even communicate English from 1,000 years ago would be as alien as Martian. The universe's safeguards might not just be about paradoxes, they could be about survival. Time isn't just a dimension, it's an ecosystem, and we're finely tuned to our slice of it. Perhaps the most persistent myth is that time travel would be solitary. From the time machine to Looper, protagonists hop through eras alone, their actions unobserved until the plot demands drama. But consider the butterfly effect in practice: a conversation overheard, a shadow glimpsed, a single footprint left behind. In a universe where every action echoes, true solitude would be impossible. Even a time traveler hiding in a cave would alter air currents, scatter dust, leave metabolic traces. The conjecture's implied veto on paradoxes isn't just about big events, it's about the impossibility of true invisibility. The past isn't a diorama, it's a living, breathing web where every thread tugs another. Finally, there's the granddaddy of all misconceptions, that time travel is a solved problem waiting for the right genius. Films love their eccentric inventors, wild-haired loners who crack the code in a basement lab. But real breakthroughs demand collaboration, peer review, and incremental progress spanning generations. Even if time manipulation is possible, it won't be a eureka moment. It'll be a mountain of failed experiments, debated theories, and incremental steps. The universe doesn't hand out shortcuts, and the conjecture reminds us of that. Time isn't a lock to be picked, it's a puzzle with pieces we're still learning to see. So the next time a movie shows a hero rewriting history with a smirk, remember, the truth is far stranger and far more humbling. Time travel isn't just about outsmarting the cosmos, it's about realizing how fiercely the cosmos guards its mysteries. And that, in its own way, is more thrilling than any Hollywood plot twist. Could the chronology protection conjecture ever be proven wrong? While Hawking's idea holds weight, the frontiers of physics are anything but static, and some emerging theories suggest nature might have loopholes we haven't discovered yet. Start with quantum entanglement's eerie behavior. If particles can influence each other across vast distances instantly, could they also communicate across time? Experiments in quantum optics have already shown that measuring a particle in the present can retroactively alter its past state, a phenomenon called quantum retrocausality. It's not quite Marty McFly revisiting 1955, but it hints that causality might be more flexible than Hawking imagined. If microscopic time loops are possible, could they be scaled up, or is the universe only lenient at the smallest scales? Then there's the wild card of dark energy. This mysterious force accelerating the universe's expansion might hold properties we've yet to understand. Some speculative models suggest that under extreme conditions, like near the Big Bang's remnants, dark energy could warp space-time in ways that temporarily sidestep the conjecture's restrictions. Imagine a cosmic backdoor where the universe's expansion creates fleeting pockets where time's arrow wobbles. These regions wouldn't last long. Hawking's quantum corrections might still kick in, but for a split second the rules could bend. String theory adds another layer of possibility. In certain higher dimensional configurations, closed time-like curves might form without triggering catastrophic feedback. Picture a universe with extra spatial dimensions curled into intricate shapes. A time traveler navigating these folds could, in theory, loop back without ever creating a paradox detectable in our four-dimensional experience. It's like hiding a wrinkle in a rug's pattern, visible from one angle, invisible from another. Critics argue this is mathematical sleight of hand, but if extra dimensions exist, who's to say time can't thread through them? Even black holes, those enforcers of cosmic order, might harbor exceptions. Rotating black holes known as Kerr black holes have ergospheres where spacetime gets dragged so violently that exiting might land you in a different time. While Hawking radiation would still pose a threat, some calculations suggest that sufficiently advanced civilizations could harness these regions as natural time machines. The catch: you'd need to survive tidal forces strong enough to spaghettify a planet, and the universe might still glitch the system to prevent paradoxes. The most radical challenge comes from the holographic principle, which suggests our 3D reality is a projection of information encoded on a 2D surface. In this view, time might not be fundamental at all, just an emergent property, like temperature arising from atomic motion. If true, tampering with time could be like editing a movie script rather than rewinding the film. The conjecture's safeguards might simply not apply in a universe where time is an illusion. None of this proves Hawking wrong yet, but it underscores how much we still don't know. Every time we think we've pinned down nature's rules, it reveals new layers of complexity. The Chronology Protection Conjecture isn't a death knell for time travel, it's a challenge to dig deeper. After all, physics has a habit of turning impossible into not yet. Just ask anyone who once believed the atom was indivisible. Time travel captivates us because it speaks to something fundamental in the human experience, our longing to rewrite regrets, witness history firsthand, or glimpse the future. Yet, as we've seen, the universe might have other plans. The Chronology Protection Conjecture isn't just a footnote in theoretical physics. It's a bold declaration that reality has safeguards. From Hawking radiation frying time machines to quantum fluctuations erasing paradoxes before they form, nature seems fiercely protective of cause and effect. But here's the twist: this isn't a story about limitations. It's about how the cosmos maintains the very consistency that makes existence possible. Without these cosmic guardrails, the past could unravel like a fraying rope, and the future might dissolve into chaos. The debate isn't settled, though. For every argument supporting the conjecture, there's a tantalizing loophole: wormholes threaded with exotic matter, multiverses branching around our choices, or quantum retrocausality bending the rules at microscopic scales. What's remarkable isn't just the science, but what it reveals about us. Our fascination with time travel isn't really about machines or equations. It's about our deepest hopes and fears. We want to believe we're not bound by time, that our choices could ripple across centuries, that second chances aren't just fantasies. Yet the universe whispers back, some boundaries might exist for a reason. So where does that leave us? Maybe time travel's greatest gift isn't the promise of adventure, but the questions it forces us to ask. What does it mean to live in a universe where the past is immutable, the future uncertain? How do we find meaning if we can't rewrite our mistakes, only learn from them? The Chronology Protection Conjecture doesn't rob us of wonder. It grounds that wonder in something even more profound: the fragile, fleeting beauty of a timeline that's ours alone. Now over to you. If you could bend time's rules just once, where or when would you go? Or do you think the universe is right to keep history under lock and key? Drop your favorite time travel theory in the comments, and let's keep the conversation stretching across time. After all, even if we can't visit the past, the future is still wide